Discovery is about to experiment with a variety of volatile elements known as the alkali metals.
First, we'll delve into the periodic table and see what makes this collection of chemicals so reactive in exploring alkali metals.
Then we take to the skies to see how metal alloys ushered in a new era in flight in lithium aircraft alloys.
Next, we travel to an island community to see how removing salt from the ocean makes fresh drinking water in sodium, salt from the sea.
Then we explore the role played by one alkali metal in timekeeping and GPS equipment in cesium, atomic clocks.
And finally, we'll examine how alkali metals and other elements are used to create spectacular aerial displays in the Insider's Guide to Fantastic Fireworks.
Exploring and exploding the alkali metals, coming up next.
As you watch the first half of this program, keep these questions in mind.
What properties do the alkali metals share?
What makes the alkali metals so chemically reactive? The alkali metals can be the most dramatic group of elements on the entire periodic table. These chemicals are so reactive that they interact with most other elements they come into contact with. And some of these interactions can be explosive.
What do you know about the alkali metals?
The alkali metals are the most reactive compared to all other elements in the periodic table.
Sodium, one of the alkali metals, likes to bond with chlorine and make table salt.
The alkali metals I know they're just the first group of metals. They're part of the S group.
They're not very strong, and then they're more likely to bond with other elements and form compounds than to just float on their own.
The alkali metals are soft metals that tarnish rapidly, even in dry air. They have lower melting points and lower densities than most other metals. They all react violently with water, and as a result are never found uncombined in nature. Lithium is the least dense of all the metals. It is sometimes used to make lightweight steel alloys for high-performance aircraft. Sodium is the sixth most abundant element on Earth. Its many uses range from table salt to batteries, and it is one of the main components in seawater that makes it undrinkable. Potassium is the seventh most abundant element on Earth. It goes into glass, soap, and explosives. Rubidium is used in photoelectric cells, vacuum tubes, and heart research. Cesium, a rare element, particularly reacts with other elements. Scientists use it to help calibrate atomic clocks. And francium is possibly the rarest element on Earth. It is very short-lived and occurs as a radioactive byproduct of uranium decay. There is less than 1 ounce of francium in the Earth's crust at any one time. Like most other metals, the alkali metals are silvery metallic solids. They are excellent conductors of electricity and heat. The alkali metals are very reactive, and they easily form compounds with other elements. These compounds are generally alkalis, which are capable of neutralizing acids. Because they are so reactive, the alkali metals are never found uncombined in nature. In their pure forms, the alkali metals must be stored under oil or kerosene to keep them from interacting with oxygen or water vapor in the air. The alkali metals are as soft as cold butter and much less dense than most other metals. Lithium, sodium, and potassium are even less dense than water, so they will actually float. Coming into contact with water, alkali metals interact to form oxides or hydroxides, hydrogen gas, and heat. When lithium is placed in cold water, it melts quickly and moves around the surface of the water, fizzing. And this reaction becomes increasingly violent as you go down the group of alkali metals. Cesium is so reactive that it explodes when exposed to water. Looking at the periodic table can help explain the reactivity of the alkali metals. On the periodic table, the elements are listed in order of their atomic number. The atomic number represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is also surrounded by an equal number of electrons. And as the atomic number increases, generally so does the size and mass of the atoms. As you read the table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. For example, there are 4 electron shells in an atom of potassium, so it lies in period 4. Meanwhile, an atom of cesium in period 6 has 6 electron shells. As you read the table from left to right, the vertical lines of elements are called groups. Elements in a group have the same number of electrons in their outermost electron shells. These outermost electrons are called valence electrons, and they dictate how elements interact. Elements in the same group generally interact with other elements in similar ways. None of the elements greater than atomic number 83 are completely stable. All of these elements, including francium, are radioactive. All alkali metals reside in group 1 because they each have only 1 electron in their outermost electron shell. Because atoms need 8 electrons in their valence shell to be stable, the single valence electron in the alkali metals makes them very unstable, and they easily lose this electron to other elements. Generally, as you move down through a group, the atoms' hold on their valence electrons becomes weaker. So as you move from lithium to francium, each element is more reactive than the one before it. Did you know, when pure lithium, sodium, or potassium are exposed to air, they darken and form metal oxide deposits which quickly cover the exposed metal. But rubidium, cesium, or presumably francium react violently with oxygen to form metal oxides that can spontaneously catch fire.
The first planes to take flight were made of wood and could only carry a few passengers. But the introduction of metal alloys containing lightweight elements such as lithium made it possible for nearly everyone to experience flight firsthand.
What do you like or not like about flying?
I like the whole fact that you're going somewhere new or somewhere that you have been before, but you're going to a different place.
I like looking down through the window at night.
To tell you the truth, I've always been a huge fan of airplanes, and ever since I was a little kid, I've had model airplanes, and it's always been such a thrill for me to go on an airplane.
I actually like the food on airplanes. It's very enjoyable.
The plane food is always horrible, and I guess it's always cold on airplanes because they can't, because they're so high up that it's freezing, it's cold outside, and the fact that your ears pop on landing and takeoff.
I like an airplane when you're taking off and the forces are really pushing against you and you can really feel it as you're going up in the air and you're going all like that.
I get a little queasy sometimes when I take off and land in airplanes, so I don't really like that part.
When I was little, my older brother and I were on a plane with my parents and it had a lot of turbulence, and we thought it was a roller coaster ride, and then it was a lot of fun. My parents were getting sick.
The seatbelt never fits correctly.
When you're up there in the air, sometimes you can't get the thought of crashing out of your head, and when that happens, it's a scary experience.
It's breaking some kind of laws that people once held to be true, that you can't fly. So, I look at those guys in history who said you can't fly, and I'm like, shut up, I'm flying.
Element number 3 on the periodic table is lithium. The atomic symbol for lithium is Li. Lithium, a soft silver-white metal, is the lightest of all the metals. Its density is only about half that of water. Lithium gets its name from the Greek word lithos, which means stone, because it was first discovered in mineral deposits. Lithium is classified as an alkali metal and lies in the periodic table's second row, called period 2. Each atom of lithium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of lithium, its nucleus has 3 positively charged protons plus 4 uncharged neutrons. There are 3 negatively charged electrons to balance its 3 protons. These electrons are found in 2 shells that surround the nucleus, which can be visualized as being built up from the nearest preceding noble gas, helium. Helium has 2 electrons distributed in a single electron shell. Lithium's additional electron is found in a spherical 2s orbital shell. Like the other alkali metals, which also have only 1 valence electron, lithium reacts easily with other elements by losing this electron. In this experiment, 1 gram of lithium metal is held inside a glass vial. When the vial is smashed, the lithium falls into a bowl of water. It reacts vigorously with the water to produce milky white lithium hydroxide and hydrogen gas, which can be seen here as bubbles. Since lithium is only about half as dense as water, the metal pieces actually float on the surface and are pushed around by the escaping hydrogen until they are consumed. While lithium is highly reactive, it is the least reactive of all the alkali metals, so the heat and steam it produces is not enough to ignite the escaping hydrogen. Industrially, lithium is used in lubricants or combined with other metals to increase the strength of metal alloys. It is used to make batteries, such as the ones inside many cellular phones. Also, if properly prepared by medical professionals, lithium salt can act as a stimulant in the human brain and is often used to help relieve depression. Today's high-performance jet airplanes have come a long way since the first airplanes flew more than 100 years ago. When the Wright brothers first took to the skies in 1903, their Wright Flyer was made mainly of spruce and bamboo. Wooden aircraft were successful during the early days of flight, but the strength of wood limited their size, the weight they could carry, and how fast they could go. Soon, aircraft designers turned to building aircraft out of metal. Metals improved airplane stability, increased their strength-to-weight ratio, and greatly improved their performance. Aluminum is a widely used metal in the aircraft industry because it is light and it resists corrosion well. But aluminum is too weak and bendable to be used by itself in many airplane parts. So other metals are added to aluminum to make alloys that are harder and stronger than aluminum on its own. The chemical properties of lithium make it an excellent metal to add to aluminum. Since lithium is the lightest metallic element, its alloys are also very light. But they are also very strong and resistant to fatigue. This combination of toughness and lightness make aluminum-lithium alloys a good match for aircraft. Aluminum-lithium alloys are expensive to create, so commercial aircraft use them mainly in parts that need to be exceptionally strong and light, such as wing edges and seat tracks. Aluminum-lithium alloys are used more often in the bodies and armor of high-performance military aircraft, where its high strength-to-weight ratio helps jets, helicopters, and other vehicles deal with the extreme stresses they are put under. Aluminum-lithium alloys are also used even higher up, in space. Space vehicles and satellite systems need lightweight alloys because every kilogram of weight saved can be vital to a mission's success. Aluminum-lithium alloys also react well to cold, so they can be used in the fuel tanks that help propel rockets and the space shuttle into orbit. So, thanks to the unique chemical properties of lithium, the sky is most certainly not the limit. Did you know? During a flight, fresh air is circulated through the cabin every 5 to 10 minutes. Hot air passing through the jet engines is filtered into the cabin through air conditioning units. To keep the pressure constant, a pressure valve releases air from the cabin at the same time, resulting in a constant airflow.
We need water to survive, But not all the world's water is drinkable. Most of it is salt water, which is unsafe to drink because it contains too much sodium and other chemicals.
What other things can make water undrinkable?
Oils and chemical waste can pollute the oceans and water all around the earth.
Sewage.
Sometimes it's illegal and it's through actual pipes from the factory that dump toxins into the rivers.
Toxic chemicals, nuclear waste, garbage being dumped.
Sometimes, though, it actually goes through the groundwater.
Any kind of fertilizers that are being used on farms.
The acid rain.
I guess just people, like when they're at the beach, they just litter a lot.
Element number 11 on the periodic table is sodium. The atomic symbol for sodium is Na. Sodium is a soft silver-white metal that oxidizes quickly in air and reacts explosively with water. Sodium's unusual atomic symbol, Na, comes from the word natrium, the Latin name for one of the compounds sodium is found in. Sodium is classified as an alkali metal, and it lies on the third row of the periodic table, called period 3. Each atom of sodium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of sodium, its nucleus has 11 positively charged protons and 12 uncharged neutrons. Sodium has 11 negatively charged electrons to balance its 11 protons. These electrons are found in 3 shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, neon. Neon has 10 electrons distributed in 2 electron shells. The single additional electron in sodium is found in the spherical 3s orbital shell. Sodium, like the other alkali metals, is highly reactive and loses this lone valence electron readily. Pure sodium has a silvery white appearance, but tarnishes easily in moist air. Sodium must be handled with gloves because it is highly reactive with water and can easily cause burns. Here, 50 grams of sodium are loaded onto a device on a platform floating on a lake. The device has a pail of water and a hinged arm holding a crucible above it, which can be released from a safe distance. When the sodium is dropped into the water, it will instantly generate a large amount of heat and release a cloud of hydrogen gas. The hydrogen gas will rise and mix with oxygen in the air to form an explosive mixture. The heat from the reacting sodium then ignites the hydrogen and the mixture explodes. The same experiment was repeated at night using 200 grams of sodium, and the reaction is even more spectacular. The compound sodium chloride is the chemical name for table salt, an important part of our diets. Sodium is used to make batteries and glass. Sodium vapor goes into streetlights, and liquid sodium sometimes cools nuclear reactors. Sodium is also used in agriculture and medicine. Island life has definite benefits for people who enjoy living near the ocean. But one of the drawbacks of living on an island is that residents must be fairly self-sufficient. If they run out of essential supplies such as food or water, it can be difficult and expensive to import them. That's just the problem the people of Santa Catalina faced when their island community began to run short on drinkable water. Catalina is an island off the coast of Southern California. Recent booms in population and tourism were great for the local economy, but also pushed the community's water supply to its limits. There just wasn't enough fresh drinking water to go around. So residents turned to the ocean to meet their needs. Anyone who has ever accidentally swallowed a mouthful of seawater knows that drinking too much of it can make you sick. It's undrinkable because, unlike fresh water, seawater contains over 70 different minerals dissolved in it. the vast majority of these minerals are chloride and sodium. Sodium atoms have an extra electron in their outermost shell, while chlorine atoms are one short of having a filled outer shell. As a result, when they come together, sodium donates its extra electron to chlorine, and they combine to form sodium chloride. Sodium chloride is otherwise known as salt. But if you can separate the salts from seawater, you are left with pure, fresh, drinkable water. The process of removing salt from seawater is called desalination, and it's just what the people of Catalina are doing. Pebbly Beach was the first commercial desalination plant. The plant uses a process called reverse osmosis. Reverse osmosis involves high-pressure pumps pushing seawater through a semi-permeable membrane or synthetic filter. As water passes through the membrane, the salts and other minerals are left behind.
What we're doing is we're taking fresh seawater, we're pressurizing it to 800 pounds per square inch, and we're pushing it through a semi-permeable membrane. It flows through this channel here that looks similar to a screen door. Then the fresh water is squeezed through this semi-permeable membrane to a wick inside and flows around and comes out the product. And all we're doing is squeezing out the fresh water. So we call it fresh squeezed water.
The semi-permeable membranes have microscopic holes that allow the smaller elements, such as hydrogen and oxygen, to pass through. But the larger molecules of sodium and chloride are stopped in their tracks. For every 30 gallons of seawater pumped into the plant, about 9 gallons of drinkable water come out. The leftover salts and other materials get pumped back into the ocean. This desalination plant produces about 200,000 gallons of drinkable water every day. That's about 20% of the island's total drinking water. And it's all courtesy of our growing understanding of the unique chemistry of seawater. Did you know? Humans and other animals have an inherent taste for salt, which is an essential nutrient in our diets. But most Americans eat more than twice the recommended amount of sodium each day. Too much sodium can lead to high blood pressure and other health problems.
The element cesium plays an important role in calibrating atomic clocks and global positioning systems. The accuracy of cesium atomic clocks allows satellites to calculate the location of a GPS device anywhere on the planet. As GPS equipment becomes more affordable and more portable, getting lost may soon become a thing of the past. If you were lost in the woods, how would you find your way?
Seeing that I have supplies, if I were lost in the woods, I'd probably look in my rucksack to see if I had a compass.
I think the first thing to do would be think about the position maybe of the sun.
I would watch the sun rise in the east and know it sets in the west and find my direction from that.
If I saw some light, I would walk towards that, or if I saw someone there, I'd ask for directions.
I would look for moss because I hear that moss grows on the north side of the tree.
A compass would be a logical way to get out, but I would use a cell phone.
Like, I was in there for a really long time and I couldn't find like the stars because the trees are too big, or like there was no moss because it was the middle of winter. I'd try to like walk in a straight line and like try to leave footprints.
Just keep on walking.
Sit there and yell?
Element number 55 on the periodic table is cesium. The atomic symbol for cesium is Cs. Cesium is a pliable silver-white metal. It is the most alkaline of all the elements and one of only 3 metals along with mercury and gallium that are liquid at room temperature. Cesium gets its name from the Latin word caseus, which means sky blue, the color cesium produces when viewed through a spectroscope. Cesium is classified as an alkali metal and it lies in the periodic table's 6th row, period 6. Each atom of cesium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of cesium, its nucleus has 55 positively charged protons plus 78 uncharged neutrons. Cesium has 55 negatively charged electrons to balance its 55 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Cesium has 1 more electron than xenon. This single electron is found in the sphere-shaped 6s orbital shell. Cesium, like the other alkali metals, is highly reactive and loses this lone valence electron readily to other elements. In this experiment, 1 gram of cesium is contained in a glass vial and attached to a device which can be operated from a safe distance. When the vial is smashed, it releases the cesium into a bowl of water. Cesium reacts very rapidly with water to form a colorless solution of cesium hydroxide and hydrogen gas. The reaction creates a large amount of heat and is so energetic that most of the water is hurled out of the bowl by the resulting explosion. Cesium is extremely reactive. It explodes when it comes into contact with cold water, and it even reacts to light rays. As a result, this element is often used in infrared lamps, optical instruments, and photoelectric cells. Cesium compounds are used to make glass and ceramics. And cesium-137, a radioactive waste product of nuclear reactors, is sometimes used to kill certain kinds of cancer cells. The first widely used mechanical clocks of the 1500s used coiled springs to keep time. But these clocks were not very reliable. They could gain or lose as much as 15 minutes a day. By the mid-1600s, the invention of the pendulum clock improved our ability to keep time. Pendulum clocks could keep time to within 15 seconds a day.
24 minutes, 40 seconds.
But early clocks were nothing compared to the atomic clocks of today. The most common atomic clocks use the element cesium to keep time. Cesium atomic clocks measure the vibrations of the outer electrons within a beam of cesium atoms. Cesium atoms vibrate steadily at more than 9 million cycles per second. As cesium atoms pass through a magnetic field, the frequency of their vibrations can be used to calibrate the ticking of a clock. The first cesium clock was put into operation in England in 1955. Scientists estimate that it will gain or lose less than a second every 3 million years. And newer cesium clock designs are even more accurate.
At the tone, Eastern Daylight Time, 15 hours, 54 minutes, exactly.
The U.S. Naval Observatory operates about 70 atomic clocks. The average of these atomic clocks creates the master time signal that is broadcast by satellites circling the Earth. Navy ships depend on this system for navigation. The system is called GPS for Global Positioning System. It depends on 24 Navstar satellites that circle the globe in synchronized orbits. The satellites send information to the receivers on Earth. Each signal arrives at a slightly different time depending on the distance of the satellite. The GPS receiver computes the time delays and can figure out a satellite's location. GPS is finding its way into new places. GPS receivers are helping lost hikers find their way, synchronizing the distribution of power, and assisting mass transit vehicles in avoiding collisions. And many cars are coming equipped with talking navigation systems too. So, thanks to cesium clocks and GPS, more people will be able to get where they need to go, and get there on time. You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
What properties do the alkali metals share?
What makes the alkali metals so chemically reactive?
If you'd like to learn more about what you've just seen, go online or check out these books at your local library.
As you watch the second half of this program, keep these questions in mind.
How are fireworks projected into the air?
Can you name some elements in fireworks and the functions they serve? Every July 4th, America celebrates its independence with parades, picnics, and fireworks. Millions of Americans across the country gather to watch these dazzling displays of chemistry in action. For them, the 4th of July just wouldn't be the same without this important ritual.
What rituals do you perform?
My basic ritual with my family is that we usually go out every weekend.
Every single Friday, we always have pizza and soda that night.
We wear this face paint because it's supposed to be intimidating and it's a form of team spirit.
Night before soccer game, I put my cleats out and my uniform and everything, make sure everything's perfect.
One of my rituals is putting on eye black before a game, and I have to listen to Nirvana and Guns N' Roses just to get my blood pumping.
Every weekend I walk my dog in the park.
Every Sunday morning, my parents and I go out to brunch.
It's the need to have huge family parties as opposed to just a small get-together.
Christmas, we'll all go to church together, then come back, open gifts at midnight, watch old family videos.
I actually go to church every Sunday.
Every couple of months we clean out the garage, or my mom makes us clean out the garage.
My most important ritual would definitely be Rabbit Day. It's the first of every month, and before you do anything, you have to turn your pajamas inside out and run around your bed 3 times saying Rabbit, Rabbit, and then that starts my month off right.
It's called artificial fire. It's an explosive chemical cocktail that can ignite the whole sky with color. What goes on inside a firework? How can 1,000 shells burst in perfect time to music? And why do we love to look at them so much that our brain cells dance with pleasure? Get ready to see fireworks in a way you've never seen them before. Fireworks can rock you, delight you, or put you in a trance. On July 4th, Americans claim their inalienable right to see the rocket's red glare. In Ojai, California, the celebrations have hardly changed for the past 50 years. During the day is a street parade. But the celebration is all about what happens at night, fireworks. Tonight, the sky will fill with almost 1,000 incendiary devices in complex, glorious acts of pyromania.
This is where all loose threes that we didn't have.
It takes a dedicated crew of pyrotechnicians one whole day to make sure everyone gets enough oohs and ahs.
For being small town as we are now, this is something special for them. This makes it the day of happiness. This is their show.
Stern Ingham, a professional pyrotechnic operator, is a veteran of Ojai's annual celebration.
Well, the idea is to get the fireworks in the air, and what we try to have is something going off all the time. Now, naturally, there'll be a few lulls, but you don't want breaks. We'll run 20, 25 minutes, something like that.
The fireworks won't just be painting the sky, they'll be lighting up the ground, too.
This is a set piece in between shooting the fireworks. We'll stop and light one of these and let it burn out and then start again.
Rigged incorrectly, these fireworks could cause a disaster. That's because there's more than a ton of explosive material in this field. And for this show, the crew will be directly in the firing line.
You got rope ready? So they're gonna light this one right over there?
Probably the one in the front.
At this show, these people like to hand fire them. In other words, they have a fusee or a lighter, and they light each fuse manually.
A hand-fired show is a rarity in these days of computer-controlled fireworks. But it's the Ojai tradition.
There's an adrenaline rush that goes with this that is unlike any other adrenaline rush out there. You can drive a motorcycle on the freeway at 190 miles an hour. You can do all kinds of things to have an adrenaline rush. This is unlike any of those.
Tonight, 15,000 spectators will experience a glorious spike of adrenaline if the finale goes as planned.
This will probably go up in about 35 seconds, maybe less. You're looking at, just in 3-inch shells, you've got over 300 rounds. We've got, I believe there's a 4-inch there. There's a combination, so that's 6 and 5, and then 4 more over here. So you're looking at 300 and change shells in 30 seconds or so.
Amid the smoke and noise of battle, someone's going to have to keep the firing crew on track.
I try to envision what's going to happen, and I try to communicate that to the crew. The only way to do it is yell at them.
Time to set fire to the sky.
First one.
Burn some shells, man. Finish that front row. Fountain! No! Fountain! The front row. Okay, we're done.
The show was a hit with the crowd, if not 100% success for the crew.
It didn't go as well as expected. Just the finale didn't happen the way we had planned. We had some breaks in the fuses and just couldn't catch up to them. So we lost about 60 or 70 shells out of the finale. It just happens. There's nothing we could have done. It just blew.
This faulty fuse meant several dozen fireworks were left sitting in their mortar tubes.
These didn't go off, so we're going to have them soak them in water and render them safe, so they'll no longer be an explosive hazard here.
You've got to treat unexploded fireworks with extreme caution.
It's in. It's in.
But that's part of what we love about fireworks, their unpredictability. This night, as on every July 4th night, tens of thousands of fireworks will illuminate the American sky. Explosives worth more than $200 million will burst into light and smoke. What is the timeless lure of these bursts of light, these chest-thumping explosions? The story began 1,000 years ago. 2 Chinese alchemists were busy trying to create an elixir of life, adding various tonics and powders to a bubbling cauldron. A few moments later, they had fire on their hands. A catastrophic accident turned into a stroke of cosmic good luck. They had unwittingly created mankind's first explosive, black powder. Mix charcoal, saltpeter, which is sodium nitrate and sulfur, and grind to a fine powder. The recipe is still used 1,000 years later inside common firecrackers. Once a fuse burns into a mass of black powder, an incredibly rapid chemical reaction takes place. Saltpeter acts like gasoline to the flammable mixture of sulfur and charcoal. The result is a hot gas under so much pressure that within a few milliseconds it blows the cardboard tube apart.
No matter where you are, in any part of the world, if there's a Chinese New Year celebrations, that is the sound of the firecrackers.
Firecrackers are as much a part of Chinese culture as the Great Wall and Tai Chi.
The firecrackers are used basically is because of the loud noise they have, and they believe the loud noise is able to get rid of the evil spirit.
Few modern Chinese believe firecrackers chase away evil spirits, but most people are still captivated by their power. What is the chemical magic going on inside a firework? Movie pyrotechnician Thane Morris, whose credits include Raiders of the Lost Ark and Star Wars, makes it his business to know. This is an exploding firework filmed at 1,000 frames a second, or 30 times normal speed.
That's a
2.5-inch aerial shell, approximately 1 millisecond. You can see it start to break the shell open. Within 2 more milliseconds, you'll see the shell completely opened up. You can see the stars being fired out of the aerial shell. Expansion of the gases and the heat is what causes the aerial shells to break open and spread the stars around at a very high speed.
Balls of fire called stars are captured here as they shoot out at around 300 miles per hour.
This is another 2.5-inch aerial shell. We shot this one in the dark. We get some overexposure at the very beginning, showing the extreme temperatures involved, very hot, 4,000 degrees. As the star burns, you can see the metal material burning off of it. It's aluminum or magnesium that's normally used in stars to create that look.
Thane Morris has to know how to harness the devastating power of fireworks with split-second timing. His job and his life depend on it.
This is a device we make. It's called an SB-20. It's designed for one purpose and one purpose only, to make loud noises. This whole action is taking place in less than 100 milliseconds.
The explosive substances inside fireworks have devastating energy locked away in their chemical makeup.
When you see this thing fire, you see the shock wave coming across the bottom of it. It's actually lifting debris off the ground. As you see in nuclear explosions, when they fire a hydrogen or atomic bomb, you'll see the same sort of action in a much larger scale.
Italian cities often hosted pyrotechnic parades where plaster cast figures spewed fire from their eyes and mouths. Some of the direct descendants of those medieval pyrotechnicians are now based here in Cincinnati, Ohio. Rozzie's famous fireworks has been making sky fire for over 100 years. The Rozzies are a fireworks dynasty. While some companies talk about business being explosive, for the Rozzies, that's no exaggeration. Art Rozzie manages the plant. And his father, Joe Sr., is a living link to centuries of pyrotechnic tradition.
My father told me how not to do things. It gets in you. You know the right way and the wrong way.
You have to like to do it and do it right as you can, as right as you know how to do it. So my father taught us. My father's very good at it. He was excellent at it. So he passed that on to us.
The Rozzie factory may look ramshackle, but appearances can deceive. The workers are constantly on guard against static electricity, their #1 enemy. One tiny spark can spell catastrophe, so each building is armed with a grounding plate to keep a dreaded spark at bay. These flimsy shacks are built to fall apart in an explosion, reducing injury from the concussion of a blast. They are spaced far apart to prevent fire from spreading. The basic ingredient of all fireworks is a ball of fire called a star. At the Rozzies, they're made in the old-fashioned way. That means by hand. First, you mix the chemicals together and press them into a shape. Then add a coat of priming mixture to make sure they catch fire as they hurtle through the air at hundreds of miles an hour. Of course, to have the proper effect, you've got to do more than make stars. You've got to launch them into the air. This is the beginning of an aerial shell, the most common pyrotechnic device today. Packed with stars and a bursting charge of black powder, it's designed to be fired from a mortar tube. A packet of black powder, the lift charge, is taped to the bottom of the shell. When it lights, a violent explosion fires the shell into the air at around 400 feet per second. Then a second fuse ignites the core of the firework. That blows the shell wide open, sending glowing stars in all directions. This classic floral pattern, invented in Japan 300 years ago, is called the chrysanthemum, but there are dozens of variations. Want to know how they make them? Take a chrysanthemum and replace the stars with a slow-burning variety, and you get this, the weeping willow. Take a tube full of stars and fire them one at a time into the air, and you have a Roman candle. Add sodium salicylate to stars and the resulting hot gases to create a warbling, whistling sound. Fill a firework with magnesium or aluminum dust, and the result is this. Arrange the stars just right inside the shell, and you can draw shapes with fire. The most complex of all the shells is an Italian classic, the multi-break.
Multi-break, yeah. We used to make a lot of them years ago, 3-break, 4-break, 5-break, 6-break. It's so much work. If you made them right, it took so much work to make them, You had to follow on one break at a time.
But they're still made in limited quantities. This is really 3 or 4 fireworks in one. The cylinder is divided into layers of stars, each with its own bursting charge of black powder. Between layers are timed fuses called spoulettes that create pauses between the explosion of each layer.
After we finally set that spoulette to the correct height, it's then ready to be spiked.
Spiking, or wrapping the shell in string, keeps the contents tightly bound to maximize the explosive burst.
Now we have to spike it again.
Each shell is a work of art, a painstaking work of art.
You wind this up just like you're winding up a barber pole, and I go on up to the top of the shell, making little squares like that till I finish off at the top.
In a typical multi-break shell, the bottom layer of stars breaks first. What's left of the shell keeps on going until the spoulette burns through to the second layer. Finally, a charge of aluminum dust caps off the sequence with a bright flash and a deafening kaboom. After a few multi-break shells, the whole sky fills with fire. Fireworks families like the Rossis have built their empire on chemical secrets passed down through the generations. These recipes for explosive magic are still kept under lock and key. But times are changing. Now others are figuring out the arcane formulas for creating color. You make red by infusing the explosive mix with strontium ions. Green, one word, barium. Blue is the calling card of copper. To stay ahead of the curve, the Rossis have accelerated their expertise from chemistry to choreography.
Years ago, you used to shoot aerial shells one at a time. Now you shoot a lot of them electronically. Before, people had to be satisfied with waiting for that one shell to go up and go up. Now you don't have to wait any longer. They get them up there fast.
A typical show now calls for thousands of aerial shells bursting in time to music. Thank goodness for computers. Forget black powder fuses. Now they use electrical wires. When hot with current, a small strip of wire inside the lift charge rockets the firework skyward. Each firework is numbered and electrically linked to a switching box, which is connected to a computer that can fire any firework at any time, or dozens at one time. Each Labor Day, the Rossis toast Cincinnati, their hometown, with Riverfest. It's a fully electronic choreographed musical show that burns through 8,000 shells in 30 minutes.
We like to knock the audience off their feet also, but you don't want to do it the whole show. You want to show them some beauty. You want to show them, you want them to think about an individual shell, and then you want to rock them.
But Art Rozzi wants to make these shows even more spectacular to bring fireworks and music into perfect harmony. This is a standard time fuse that sits inside an aerial shell. And this is the Magic Fire chip. This techno wonder makes sure that each firework detonates at exactly the right millisecond. Normally, a black powder fuse starts burning the moment a firework launches from its mortar. It blows the shell apart after 4 or 5 seconds. A Magic Fire chip programmed to light the burst charge after 5 seconds will light it after precisely 5 seconds.
Theoretically, you can shoot something in the sky exactly where you want it, the exact effect you want it, at the exact time.
So today, the Rozzis are planning a full-scale show to test Magic Fire's precision choreography. Art's younger brother, Joe, keeps the rigging crew from crossing their wires.
It's all the control cable that'll run data and power out to the firing sites. These are the main controllers that interpret the data coming in from the laptop that basically tell the system out in the field what to do and when.
For Art Rozzi, the work began several days ago when he began to choreograph the show to a fireworks standard, the William Tell Overture.
Right after the intro, there's a loud percussive piece that we're going to use big salutes to augment it. Well, we're going to hit these percussion with salutes with the Magic Fire technology.
Art is saving the toughest test of Magic Fire for last, a series of over 50 shells timed to musical beats.
Generally, on a traditional show, the finale, you just light it and let it go. This is just a little different. We're trying this technology, and it's developing technology.
With more than 400 microchip-controlled shells, it's going to be a historic high-tech fireworks display.
It's very tightly choreographed. We have about 400 shells here that'll fire in 3.5 minutes, which up until the introduction of the chip technology was fairly impossible. You shoot 3 shells from 3 different places, and they may break kind of scattered. To us, we see 3 shells break together. It's a wow moment.
Great fireworks shows are more than the sum of their parts. Will technology inspire a pyrotechnic rhapsody?
Everything fired wonderfully. The colors were vivid. It was a nice, cool, crisp night. Colors came out perfect. Magic Fire worked perfect. You could tell all shells firing from 3 locations all broke at the same time. There was no boom, boom, boom. It was boom, all together.
You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
How are fireworks projected into the air?
Can you name some elements in fireworks and the functions they serve?
We hope you've enjoyed this assignment discovery analysis of the alkali metals. If you'd like to learn more about what you've just seen, go online or check out these books at your local library.